Greetings everyone. In the last video I worked on the 3.408 gigahertz LO source that once multiplied by 3 will get me to 10.224. That multiplication by 3 can easily be done, as I showed you, with an MMIC amplifier and actually a few amplifiers, because we need to boost that 10 gigahertz harmonic and filter in and filter out all the other harmonics. Well, it happens that Paul Wade, W1G8Z, has a PCB that does exactly this, and he distributes that PCB. It's 3 amplifiers, MMIC based, and 2 pipe cap filters. And he distributes the boards for his projects at a very reasonable cost. It's bare boards though, so you need to buy all the components, including the pipe caps and the connectors and everything. But that's a good starting point. Instead of designing it myself, why not ordering the bare PCB? Which I did. And another board I've ordered from him is the simple and cheap transverter for 10 gigahertz. And it's basically 2 strips, a receive strip and a transmit strip, all at 10 gigahertz, a mixer, and several stages of amplification. And of course, pipe cap filters, 4 in total. So that's another proven, tested solution that I will adopt. So I have also ordered this bare PCB and 2 double balance mixers from him as well, but everything else I purchased separately. So until these 2 boards come in, I've decided to cut my teeth on pipe cap filters. And this is a prototype I built with a piece of double-sided PCB. It's the half thickness PCB, so only 31 mils, so 31 thousandths of an inch, instead of the 62.5 usually. That's a more common PCB thickness. So this one is thinner, which allows to have thinner tracks on either side, and that tracks widths that match the pin of the connectors as well, and 0805 components. What I did is I cut off lines with a very sharp X-Acto knife and then peeled off the material. I used the same spacing as Paul for his pipe cap filter. How to build pipe cap filters is relatively easy. Paul wrote an article that explains the design of such pipe cap filter. And it's an adjustable filter with an adjustment screw here on top and a lock nut. And everything is soldered down onto a ground plane. It is, I'd say, quite easy to build. This one was really experimental, and the soldering job of the pipe cap on the PCB is not as good. As you can see, there's a bit of a gap on the solder here at the bottom, and the reason is I took it off and reinstalled it later. But normally this would be a perfect seam all around. There are 2 probes inside. So if you want to know more about pipe cap filters, I suggest you read Paul's article on revisiting pipe cap filters. And he has designs for 3.4 gigahertz, 5.8 gigahertz, and 10 gigahertz. And I just copied his design for 10 gigahertz. I've also added some copper tape on the PCB edge. It's a self-stick copper tape to bridge the 2 ground planes, on the 2 sides, since there is no vias, available. This is just a bare PCB, and I peeled off some copper. So I use this copper tape to help link the 2 sides together. I've left enough space on either side of the traces so that the copper plane doesn't really play any effect, but it does ground the connector on both sides. I used a brass nut and then soldered the whole thing, the pipe cap. It's a 1/2 inch copper pipe end cap, and some probes inside. Now for the assembly process, I followed N1BUG's technique of soldering the pipe cap against the PCB. He has a video, if you look on YouTube, N1 Bravo Uniform Golf. He has developed a technique to solder the pipe caps in a neat fashion. And I suggest you go see his videos on pipe cap filters. And that's essentially the process I used to solder the cap on here. So a bead of solder and some flux and a heating plate to help preheat the surface, and then finish it off with a heat gun to melt the solder all around. And that's it. Easy job, and it gives good results. Now let's see how this pipe cap filter behaves in frequency. So instead of doing reflection losses like I did with the transition, like the waveguide to SMA transition, I used the same script more or less, but I measured this time the insertion loss. So I inject signal and then measure on the other side of the filter, and I tried, of course, to tune the filter to peak 10.244 megahertz. You see three curves. The first measurement, I made it with a probe length of 6.15 millimeters of American wire gauge 24 size. Why 6.15? Well, it's a mistake because Paul's article talks about 3.96 millimeter probe, so roughly 4 millimeters in height above the PCB surface. But I made a conversion error and cut to 6.1 millimeters. And this is what I got. I had an insertion loss of around 6 dB. If you look here, 0 being perfect, of course, and no loss if we insert the filter in the line, which is not possible. So 6 dB, which is lower than what I was expecting. He claimed that we should normally get around 3 dB of insertion loss. So I was kind of thrown off by this response, and there was a nice peak around 3, but it was higher in frequency, around 10.75 gigahertz. So it's like if the probes were too short, basically. We wish we had this peak right here, And so being higher in frequency means that, well, it's too short in terms of probe lengths. So what I did next, because it seemed that the nice response was a little too high, still a bandpass, but too high for the peak, I cut to 7, just arbitrary, larger than the 6.15. And this is what I got. 7 brought me around 3 to 4 dB of insertion loss, which was better, but I noticed that I could get even better, lower in frequency. So I decided to open the cap and cut back to 6.5 millimeters. And also notice that for the last 2 tests, I switched to AWG 22 wire instead of 24, thinking that maybe with larger wires, it could improve something. That wire has tin plating on it. So what I got is the green plot, which indeed sits between the two. Makes sense. I shortened the probe a little bit, so it shifted up in frequency. Not quite at the absolute peak that I could get, 10.244. So theoretically, maybe I could have cut to maybe 6.75. I don't know if I can achieve that kind of accuracy in the cuts. But anyway, probably somewhere in between would have been the best place to shoot for. But, okay, I left it to 6.5 because I had, again, around 3 dB of insertion loss. So I'm not really trying to make a perfect filter. It was not a perfect solution for many reasons. First of all, if you look at the bandwidth of the filter, it's much, much wider than what Paul measured with his filters, his pipe cap filters. If you look at the whole width, it's easily 1500 megahertz, and we should expect around 1% of 10 gig, which is 100 megahertz. So the filter response is way too wide. Why exactly? I've consulted Paul and he does not know. He gave me some hints of things, such as the PCB tracks on the board, the end of the track where I put the probe, where I soldered the probe, well, maybe there's a stub. Maybe the track should end a little shorter. So that's one possibility. And another one could be maybe the connectors, because this looks like, if you look at the blue trace, it looks like there's some sort of resonance of some kind in the middle of the bandpass. And maybe this is the peak that we should have gotten. And this is in addition to the peak we should have gotten. So exactly why, I don't know. That filter was handmade, not a professional PCB. But the results make sense, except for the bandwidth of the filter. It's a usable filter, absolutely. It's just that it's wider than we should have expected. So it was fun to try this out. And of course, with Paul's boards, I will follow the recipes, exactly. And I should get the proposed results in the article. With probes of 3.96 millimeters long. So there you go, a fun exercise. See you soon, 7-3.